Yeah, I think that in 1 minute you can also start the jingle, I guess.
The following message is best viewed on an oscilloscope.
Okay, so good morning, everybody, and welcome to the third session of track 14 of ICHEP 2020. This morning we have a rich program with the contributions from Alice and Belle II and the KOTO experiment and a presentation on CMS and Kubernetes, and then other 2 talks about symbolic library for HEP and accelerating Monte Carlo simulation with data flow graphs. So without much further ado, I would welcome to this session and start with the first talk of this morning by Chiara Zampolli from CERN on Alice data processing for Run 3 and Run 4 at the LHC. So, Chiara, whenever you are ready.
Yes, good morning, everyone. So can you see me? The slides, everything is fine?
Yes.
Okay, very good. So good morning. I'm really pleased to give you this presentation in the very first session of today about the Alice data processing for Run 3 and Run 4. So this is the rich outline of my talk. So there will be a lot of material here that will be presented. And I would like to remind you that there's 3 more presentations in ICHEP this year concerning topics that are quite related to my talk, which will talk about the Run 3 and Run 4 processing. So let's start with an overview of Alice. So Alice is the dedicated heavy ion experiment at the LHC. We have Barrett tracking detectors with a geometrical acceptance in eta smaller than 0.9 absolute value, and with a full azimuth coverage. So the precision tracking of Alice allows to go down to very low momenta, below 100 MeV, and also to track in a low magnetic field configuration. We have a lot of detectors that are dedicated to particle identification in different momentum ranges and that span over low and high momentum. And this is really an excellent capability of the detector. And the tracking detectors are optimized for the very high multiplicity environment that we have in heavy ion. So in Run 2, the lead-lead interaction rate was 7 to 10 kilohertz, and the trigger rate of Alice was limited by the TPC readout and by the bandwidth. So here in red, you see the TPC of Alice, where it is located. And we collected a luminosity of 1 inverse nanobar during the data taking. In Run 3 and Run 4, the interaction rate will be much higher, so we go to 50 kilohertz. Clearly, we will take data also in PP, and the readout will be continuous. So this is really one of the main differences with respect to Run 1 and Run 2. The goal here is to collect 10 inverse nanobar of luminosity at the nominal magnetic field and 3 inverse nanobar at the low magnetic field. So such different data taking paradigm is possible thanks to the upgraded detectors that we will have in Alice. So in particular, the ITS, the TPC, the MFT and the fit. And there is a talk by Stefano that was given the other day. In this presentation, I will discuss a bit the TPC, because as you will see, this is the key detector for the data processing. So as a matter of fact, the TPC will move from being a multi-proportional wire chamber to a detector based on GEM. And this allows to go from the triggered readout mode to continuous readout mode. The R&D was really dedicated to optimize the configuration of the detector and its performance. And you see here the configuration that was finally chosen. But clearly, if we have a different paradigm in terms of data taking, also our data processing has to change. And this is why the online and the offline world have now met into what we call the O square online-offline processing world. So how we are going to take data in run 3 and run 4, this is a sketch of what will happen. So the detectors will send their data to the first level processors with a data rate of 3.5 terabytes per second. And in the FLPs, we will have the first level of processing, which aims at the first level of data compression. So zero suppression, for example. And then the data will go from 3.5 terabytes per second to 0.6 terabytes per second. The data that are coming continuously from the detectors will be also chopped into what we call time frames, or better, in the FLP we will have sub-time frames, because they will be only part of the detector. And each time frame is a packet of data of a fixed length in terms of number of orbits. So it will be about 128, either 128 or 256 orbits, which corresponds to about 10 to 20 milliseconds. After we have this first level of compression from 3.5 to 0.6 terabytes in the FLPs, the data, so the subtime frames, are sent in a round-robin fashion to the event processing nodes, so the EPN here. And here they are reassembled to create the full time frame for the full Alice detector. So in the EPNs, we will have the synchronous reconstruction that will take place, the calibrations, further data compression, so that then the data rate is smaller than 0.1 terabytes per second. And the data that are built in such a way are the so-called compressed timeframes, and they will be stored into a 60 petabytes disk buffer in order to be processed later on. So as you can see here, this is what will happen while we take the data. So this is what we call the synchronous processing. And this has a factor of reduction of 35. So this is here. Then we will have an asynchronous stage. And this will be a second and maybe a third processing stage, when then the reconstruction will be done with the final calibrations. And this will run on the EPN farm, so the O square EPN farm, but also on the tier 0s and the tier 1s. And the final objects that we store are the so-called analysis object data, so the AODs, and they will go into the permanent storage together with the compressed time frames. So in summary, this is what will happen. We will have a phase of synchronous processing during the data taking, and then we will have a phase of asynchronous processing. So the synchronous processing is, as I said before, what is the key role of the synchronous processing is to reduce the data of a factor 35. And here the main detector that is concerned is the TPC. That is why I firstly discussed that. So the TPC will have to go from 3.4 terabytes per second to 60 gigabytes per second. So this is clearly a big reduction. And the compression will be based on several aspects. So there will be clearly the zero suppression, then we will do clusterization. The data format in which we store the clusters will be optimized. There will be entropy reduction, but it will also rely on TPC tracking. And this is in order to remove clusters not associated to tracks, so they are sort of physics noise. And then also there will be some remaining cluster entropy compressed that will be done with the ANC encoding. In this picture here, you see examples of clusters that could be removed because either they are belonging to unwanted tracks, or they are just clusters belonging to tracks for which the fit failed, and so on and so forth. So the part of the data compression will be based on the use of GPUs, and this is quite mandatory because the use of GPUs allows to reach the speed that we need at synchronous processing for reconstructing our data. And especially there will be the clusterization and the TPC tracking that will be done on the GPUs. So in this sketch, you have all the steps that are running in synchronous reconstruction, but also those that are planned to be run at asynchronous reconstruction to make use of the GPUs at their full potential that are planned for Alice. What is very important in the studies and in the performance of our reconstruction code is the fact that the processing time that you see here as a function of the number of clusters has a linear behavior. So what does it mean? The number of TPC clusters is a sort of proxy for the duration, for the length of our time frame. And since this is scaling linearly, then it means that, the time frame length does not impact on the number of needed GPUs. And this is really important in order to set up our farm. In this very complicated sketch here, I want to emphasize one box, which is really key in the Alice data processing, and this is the TPC distortion corrections. So we are using the gem in order to reduce the ion backflow, which is the drifting of the ions back into the TPC drift volume that distorts the electric field, and as such, it also distorts the trajectories of the electrons. So you see here that the expectations for lead at 50 kilohertz for run 3 and run 4 present distortions that can go up to 20 centimeters. They are local distortion, clearly, and in one dimension, so in R, and then in R5 we go to about a few centimeters. So the strategy to correct this for the average distortion is the same as was applied for run 2. So what we do is to interpolate the refitted ITS, TRD, and TOF track segments to the TPC. And these are taken as reference point for the true position of the track. Then we collect the residuals between this reference point and the measured TPC cluster. And this is used to build the TPC distortion corrections. And then these corrections are used at asynchronous reconstruction. So the collection and the first processing, if you want, of this type of calibration is done at synchronous stage, but then it is used at asynchronous reconstruction. So what does it mean? This has a very important consequence. It means that we have to have some full ITS, TPC, TRD, and TOF reconstruction on at least a fraction of the tracks, which is enough to provide the corrections. And this is about 0.6%. So this full tracking in the central Barrett synchronous reconstruction is really a challenge for run 3 and run 4 because of several aspects. So first of all, we have overlap of multiple collisions. So in one drift time, so the time that it takes to the electrons to drift in the TPC, we will have 5 collisions in the TPC, so there will be pileup. But we should also not forget the fact that the TPC clusters will come not with a well-defined Z, but they will only have a time, and we will not have the time of the vertex because we will run in continuous mode and not in triggered mode. And in addition to that, there will be distortions. And then we have to take care of that. So what will we do? We will start with...
So you have 5 minutes left.
Yes, thank you. So we will start with clusters and the standalone tracking in the ITS in the TPC. Then we will extrapolate the TPC tracks to X equal 0, and we will assign the position Z equals 0. Then we will do track following to find missing clusters. We will refine the Z position. We will refit the track. Then we will find the matching between ITS and TPC. And finally, we will do refit in order also to attach the clusters from the outer detectors. So one more comment about the TPC space charge distortions. So we have this ion backflow, and then we will have between 8,000 and 10,000 ions that will drift in the TPC volume. This means that we will have also some space charge fluctuations, which will give about 5 to 7 millimeters of extra distortions, and we have to correct for them because intrinsic resolution of the detectors is about 200 microns. So at synchronous processing, we will use as average distortion map something that comes from simulation or a specific dedicated data taking, which will be scaled. And then we will correct the fluctuations in one dimension. But at the same time, in synchronous processing, we will collect the information that is then used for the corrections for the fluctuations at asynchronous reconstruction. So all this is done within the O-square processing model that relies on 3 layers. So we have a transport layer that is just fair and queue message passing architecture. And then on top of that, we have the data layer, which is the Alice specific description of the messages. And on top of this, we have what we call the data processing layer, so the DPL, which is the translator, what translates our computational problem into the lower level structure. So this is an example of the reconstruction in Alice based on the DPL. So you see that there is really a lot of blocks that are connected to each other. And this type of approach will not only refer to or concern synchronous phase, asynchronous phase simulation, but also analysis. So the analysis framework in Alice will be based on a data model using flat tables that you can see sketched here. And then the analysis will be described as a firm in the shape of task to keep a sort of legacy from run 1 and run 2. And then the final object will be root serialized objects. So this analysis framework or model is declarative because the user will have to declare what type of input they want to use and what type of object we will have in the output, but it will also be imperative because it will be the task of the analyzer to define the processing algorithm. And all this, so this is what the analyzer will take care of, and then it will be translated by the DPL into the hidden topology that we have with the fair MQ. So the analysis and computing model is different from what we had in run 1 and run 2 because we have 100 times more collisions to analyze, an increase in the size of about 30 times for the AODs, and the AODs will be stored, as I said, in a flat structure. So we will have also skimmed data in order to optimize the analysis, and also to be noted that contrarily to what we had in run 1 and run 2, the analysis model will not be exclusively distributed. So this because 10% of the reconstructed and simulated data will be copied into the so-called analysis facilities for tuning of the analysis code and validation. And only after that, the full data set, because it is very large, will be reconstructed and analyzed, will be analyzed on the grid. And this will be done within an organized analysis framework like we had in run 1 and run 2. So to get to the summary and conclusions, Alice is undergoing a major upgrade, and this is based not only on the detectors, but also on the data processing and the analysis framework. The synchronous stage will be the most critical one because it will be the one that will have to allow for a factor of 35 in data reduction, and the key ingredient here is the TPC. The O-square processing framework will have its foundations on 3 main layers, and they will be used homogeneously over the full data processing chain from the reconstruction to the simulation and to the analysis. Thank you for your attention.
Thank you, Chiara, for this very complete and comprehensive and clear presentation. Are there any questions from the audience? If not, I would make one. This is regarding, I mean, you spent some time in describing the corrections of the TPC distortions. I mean, this is a classical theme that has accompanied the Alice throughout run 1 and run 2 especially. And I mean, in terms of computing resources, I mean, do you have an idea of the impact of these corrections in terms of the required computing resources?
No, the data, so the corrections will be, first of all, we will collect these residuals, and this is not computing demanding. Then the corrections will be calculated offline, and but this is also something that we use in run 2, and it is not something that is critical in terms of computing time. What is critical here is more the collection of enough statistics that we need to do. So we cannot do this synchronously because we need quite some statistics to get the input for these corrections. And then the application, at least this is for the average distortions. And then the application of this is also something that is not computing demanding. I cannot tell you exactly the numbers there, but it is not something that is crucial. So clearly there will be some impact in terms of the data size of the output of this correction, not the calibration object, but what we use as input for the calibration object. And on the other side, we have the fluctuations. as I was mentioning before. So these, the 3D fluctuations for now are planned to be done. So there is, the work is ongoing in the direction of using machine learning techniques. And so this clearly has to be done offline for the full corrections, because again, we need some, the collection of enough statistics. And in addition, machine learning is more demanding in terms of computing. We cannot do it synchronously.
Okay, so even when you talk about this analysis that you do promptly on collected data, I mean,
no, this is something fast. It is based on the TPC tracking, on the global tracking. So this is more demanding. So the fact that you have to do tracking.
All right, thanks. So if, yeah, I see James raised his hand.
Yes. Yeah, hello. Thank you for the very nice talk. So I just wanted to ask about the synchronous processing, where you said very clearly that the use of GPUs is mandatory. And I'm assuming that this is also including Run 3 as well as Run 4.
Yeah. This is Run 3 and Run 4 in Alice will be processed in the same way.
Right, exactly. So, I mean, obviously for Run 3, I guess the procurement for the GPUs, as you know, it's had to be done already. But I'm guessing all this is written in CUDA, right? If it's using NVIDIA.
So I would like that Matteo that you give this yes. Chance to Matteo, because he has a presentation on that. But briefly, for now the code is quite portable, so there is the possibility to run it both in CUDA and OpenCL in order to be adaptable to different types of GPUs.
Okay, very good.
But Matteo will give you the details.
Right, thanks.
All right. I think we can move on to Matteo then. Thanks again, Chiara. And,
my pleasure. Thanks to you.
Let's start with the next talk on GPU-based online-offline resources in Alice for LHC Run 3.
Hello, everyone.
Yeah, it's Matteo Concas from Torino.
So, okay, yes, my talk will be more dedicated on the GPU-based online-offline reconstruction in Alice for the LHC Run 3. As already mentioned, during the Run 3, the LHC will deliver up to 50 kHz in LED collision, and the Alice experiment plans to record an integrated luminosity that goes up to 10 inverse nanobart with minimum bias. So in order to cope with these challenges, throughout the detector has been deployed many developments and upgrades. First of all, the aforementioned new triggerless data acquisition called the continuous readout, which will make us pass from a triggered acquisition to a stream of input data, which are split along the time dimension in so-called time frames. As you can see in the sketch on the bottom of the slide, in drift detectors like the TPC, we observe the overlap of multiple events since time is a variable on which we cut. So in the end, the result is that we will collect 50 times more event compared to what we collected with respect to Run 2, translated in 50 times more data. And to do so, we carried out upgrades across different detectors. The TPC, as Chiara already extensively mentioned, will be upgraded in order to cope with this continuous readout. Same for the fast interaction trigger. The inner tracking system will be replaced with a brand new one made out only of the 7 silicon pixel layers, and it will be placed for the forward tracking muon forward tracker in the inner barrel. So in this slide, I've mentioned also some interesting pointers to talk that have been given or will be presented during this conference. So the idea is that in order to cope with these 50 times more data, we will indeed need for data compression, which actually implies that the best strategy is to apply full online reconstruction that at these times requires online calibration, and it is in the end an extremely demanding task. So it requires a large amount of computing resources. So the strategy, the most convenient strategy that Alice is going to adopt is to offload a part of the reconstruction on GPUs, the largest that we can, in order to gain speed. So GPUs are programmable parallel devices that compared to CPUs are able to manage thousands of threads compared to hundreds of them that you have on CPU. The architecture is quite similar, and the key point is that many algorithms involved in the reconstruction are able to efficiently fit the architecture. A reminder, a GPU usually has a frequency lower than a CPU, but and the idea is that you achieve speed by processing more data per time unit. So the idea is that a GPU provides you a high throughput that translates in a faster global execution. And speaking of conveniency, the computing nodes can be equipped with 64 CPU cores, but up to 8 GPUs on each. So you buy less computing nodes to have convenience. So this is a summarizing schema. As you can see, the layout is quite similar. You have a dedicated memory and other agents. The key point is that a GPU has more arithmetic logic units, which are the processor responsible to perform mathematical operations. And this is the crucial point to decide that a GPU is better in scaling some kind of problems. So as already presented by Chiara, our online processing will be performed on the EPM farm, and the goal is to reduce raw input data from 3.5 terabytes per second down to less than 100 gigabytes per second. And this will be steered by the O2 online-offline framework that is able to support GPUs indeed, and will be performed during two phases, the synchronous phases and the asynchronous phases. And during the synchronous phases, we have the TPC as a main user, main use case, and the entirety of the TPC standalone tracking can run on GPUs. During the synchronous phase, we will operate that reconstruction plus some partial reconstruction with a subset of the data for IDS and TRD, which provides calibration information substantially. So then we will move to the asynchronous phase that is usually planned to be carried out during the no-beam periods or even during proton-proton collision, where the occupancy of the GPU is planned to, GPUs and computing resources in general is planned to be less overwhelming. And the asynchronous phase will include a full reconstruction for all detectors. And in this case, the GPUs can be also used by other detectors to operate their reconstruction. In case of possible remaining processing, this will be split in a 3 times by 1/3 strategy, times 1/3 across the EPN, Tier 0, Tier 1 clusters. And for further information, indeed, Chiara's talk we already attended, and I suggest you to attend also Michael Lettrich once. So concerning the integration of GPU in O2, our software stack has been already presented, but is basically implicitly, in a nutshell, is able to translate an implicit workload description to a topology of processes that can communicate each other, and this capability is able to run both on local machine and to scale over a cluster. So also thanks to the data processing layer, which is a dedicated layer for Alice data format. So in the end, DPL is able to support GPUs. So I can ask to, in a workflow, to run a specific computation on a resource that has a GPU on board. And I also would like to highlight that the multiple task runnings on different, since we will process multiple timeframes in parallel, the asynchronous behavior of a GPUs, in the sense that you load the data and ask for some computation and then just wait, is somehow masked by an intelligent scheduling of the time frame processing. What we have now is a baseline scenario that is somehow able to keep us up with the data rate online. So we are able, with the current setup, to cope with this with the challenge I mentioned you. The TPC tracking is on GPU and resources are full exploited during the synchronous phase. There is some room for improvements, especially in the asynchronous phase, where GPUs will not be completely used by TPC tracking, since it has been already completed. And the idea is to continue to develop and try to offload more and more possible computation on GPUs, in order either both to free resources on CPUs that can be used for other tasks, and to accelerate the reconstruction also for other detector. So the final goal, the ideal goal, is to place the whole barrel tracking on GPU. Indeed, with some intermediate state, we are already able to operate, but we will not stop to that. So in this plot that Chiara already showed, I would like to highlight two things. The first thing is that, okay, according to the legenda, the green part is what is already be implemented and ready to run. That means that the baseline synchronous reconstruction is already in place, and as you can see, is made up of many different tasks that communicate also each other. As you can see, also for the asynchronous phase, we have already a lot of piece of codes in place, but also some work is planned for the future, and is really few boxes that we already didn't start to work on. And the other point I wanted to highlight is that we are able to program against a GPU using an API framework that is capable to interface with different platforms, to support different platforms. And
sorry, I have 5 minutes left.
Okay. So we are able to support multiple, meaning AMD and NVIDIA GPU cards in the specific case. So one last remarks about programming on GPUs. As a physicist, one can be concerned about the results. I would like to spend some word on this. There are indeed, it is well known, some numerical deviation that are due to different approaches in computing some calculation. And usually when you port an algorithm on GPUs, you have to be careful in the sense that you have to try to port the algorithm that sticks as much as possible to the CPU one. So in the end, what you want to test is that the results are consistent with a certain margin that has to be negligible, and this is the case for Alice, and this is most likely the case for every good GPU translation of a CPU code. And the other point that one want to, maybe with a glance to the future, is that one want to dedicate attention is the portability of the code. It's quite straightforward to support multiple platforms nowadays, such as CPUs and different GPUs brains, but maintaining the code is another point. So maintaining a single code is better than replicating it for different devices. And indeed, the capability to do that is something that our current framework supports. And also, the ability to adapt somehow to the target architecture on which we run the reconstruction on is realized via automatic dynamic loading of the required libraries for the architecture. speaking about some results, indeed, I will focus more on the TPC since it's the most relevant use case, the one that gives also more satisfaction if you want. And the efficient usage of these accelerators in this plot is what I want to highlight is the fact that we are able to trade CPU cores for GPU cores. So depending also on the data sites in input, meaning the number, namely the number of clusters, we can scale from 40 to 150 CPU cores with a single graphic card. We can trade it. And regardless, in this case, okay, the comparison has been, this has to be pointed out, has been done on not fully optimized CPU code. The speed up observed here is also up to 200 and 300, which is quite optimistic. But in average, with a more fair comparison, we can assume, we can calculate a 50 to 100 speed up factor, which is quite the motivation for which we decided to move on GPUs. And another interesting factor is that as a function of, as the data sites increases, the number of required GPUs can remain constant, meaning that we are able, with a certain number of with less than 100 and less than 400 of these mentioned GPUs to support to operate the whole reconstruction. You can change the kind of GPUs. Sorry, I said I meant GPUs. You can change the GPUs model. Maybe the plot can scale, but the constant remain the same. So and the last point I want also to highlight somehow is this plot that shows the actual speed up of GPU computation compared to what we achieve on a CPU. And as Chiara already shown, the scaling is linear, and in terms of the time spent, but also what remains constant is that the proportion of the speed up as a function of the input data. And in most relevant use case, we reach a factor of 100 of the speed up. So I come here to my conclusions, as during the run 3 Alice will take this 50 kilohertz of level data readout frequency in a triggerlet regime called continuous readout. And to achieve this, we will operate data compression thanks to GPUs as a pivotal architecture to afford the data reduction. TPC and ITS reconstruction on GPU for the synchronous phase is the basic goal. Ideally, we aim at operating the whole barrel tracking on GPUs. TPC, which is the most relevant use case, has a speed up factor which is quite interesting, and in average can be of a factor of 10, and one GPU is capable to replace 40 to 150 CPU cores in average case. As outlook, we foresee to include more and more reconstruction on GPUs in order to use them as efficiently as we can. And we'll also are planning to investigate a broader usage of GPUs in the future, since we are developing also some related expertise and knowledge. The idea is to expand the range of application also beyond the only reconstruction, but also maybe for simulation and analysis. And one last remark is that this work has to be done somehow keeping an eye to the future of high energy physics computing and high performance computing that has to be done in view for the next runs at the LHC. Also because in a possible future, grid sites could host GPUs, and being able to already use them can indeed place us in a good spot. So thanks for the attention. This was all from my side.
Thanks, Matteo, for this nice talk. So are there any comments or questions to Matteo?
If there's nobody else right now, maybe I could jump in, Concetio.
Sure, go on, Graham.
Yeah, so Matteo, thanks. That was a very interesting talk. I wanted to ask you a little bit about the validation that you use. And obviously you're using different types of GPUs and different types of CPUs. And as you said, you're not going to get numerically identical results. So how do you do the validation? How do you know when the results are good enough? Is it like histograms that you use, or some other technique where you put it in a sort of acceptable tolerance?
So let me just jump to one slide I have in the backup. So this was meant to be for the code portability and consistency. So this is an example. This is an example that has been is quite aged, if you want, but it shows you how this comparison can be done. For instance, so in the legenda you see offline resolution and HLT resolution, which is corresponding to offline means the former CPU reconstruction, and the HLT is the new GPU reconstruction that was developed for the high-level trigger. Meaning, and okay, now there have been further developments on that. But the idea when you compare them is that, for instance, for the resolution as a function of the transfer momentum, you see that the HLT at low PT, you have an improvement for the HLT, but this is not carried out by the fact that it was performed on GPU, but by the fact that the algorithm was improved. So these deviations, okay, can be misleading, but the idea is that you want to compare the results and to show that the resolution doesn't change too much. So when you move forward with the LED, you see that the adaptation of the two curves tends to coincide. So in the end, you have that statistically can assume that these contributions, these deviations are negligible. And so yes, you do a statistical validation if you want.
Okay, thanks.
James, please go on.
Hello, yes, so thank you again for the very nice talk. So on your final slide, you made a comment about the possibility that grid sites could be in future equipped with GPUs. And slowly but surely, grid sites are adding queues with GPUs, not many at the moment. But I want to, let's say that a particular site that can be used by Alice was to install a significant number of GPUs. As things stand at the moment, with the machinery that you use, would you be able to make use of those GPUs today if the resources were there?
I'm not really sure. There still should be some pieces in place, especially for job submission. But the point is that the idea of being able to exploit grid sites is more related for different tasks, since our reconstruction is planned to run mostly on the EPN farm. There is actually no point in spending effort to operate it on grid sites. So the point is that for the moment, GPUs are being investigated for further for a broader area, but the idea is to use them for other tasks not related to reconstruction. So our reconstruction on GPU, which is what we have now, has been designed to run on our EPN cluster, not on possible grid sites with GPU. But it's very interesting what you say, because somehow it means that already we are moving toward that direction, and this somehow can motivate more, no? Because one grid site can decide to start deploying GPUs because there are some computations that can use them, and at the same time, who develops the code is more motivated, being certain that the code can run on GPU on grid sites with GPU. So is very interesting. And I wanted also to comment out, add to one comment on the question you made to Chiara before. We are able to support AMD and via also the HIP platform, the HIP platform from AMD. So not only OpenCL, but also the hybrid portable library from AMD.
Okay, thank you very much indeed. Thanks.
All right, I suppose we should move on. Thanks again, Matteo. If you have, I remind you that there is also the Mattermost channel that you can use if you want to make any additional comments and offline. Then you can also profit from the breaks that we will have. We have 2 of them, so just to have chats and discussions. So let's change a little bit topic. And let's move to Grégoire Uhlrich from Lyon, who will illustrate MARTY, which is a C++ symbolic computation library for high energy physics. So Grégoire, there?
Yeah. Hello, everyone. Can you hear me?
Yes, we can see you.
Okay. Okay, perfect. Let's share the screen. Can you see the slides?
Yeah, perfect. You can start.
Okay, so let's start. So indeed, I'm going to present MARTY. It stands for Modern Artificial Theoretical Physicist. It's a C++ framework for easy beyond the standard model phenomenology. So what I will be talking about today are calculations in high energy physics. So when you do BSM searches as a theorist, what you want to do actually is to compare the predictions of your BSM model with experimental data. And to do so, you have to calculate some theoretical quantities, so transition amplitudes, cross sections, and Wilson coefficients if you study an effective field theory. I will explain just next what they are. And often you need one loop level quantities, because first you want to have more precision than the tree level ones, and secondly because some of the processes you want to study are simply 0 at tree level, so you really need the one loop calculations to have a complete description of all those quantities. Those calculations are very involved and error prone, and so in general you don't want to do them by hand, and this is why we need automated BSM calculations. A word for Wilson coefficients. So we use them in particular in flavor physics. You know that we cannot observe quarks as single particles. They are always in bound states, hadrons. And we don't know really how to compute in a systematic way amplitudes with hadrons. So what we do is going to a low energy effective theory where high mass particles are integrated out. And this gives what we call effective operators in an effective Hamiltonian. And then an amplitude is just the matrix element of this Hamiltonian that has 2 parts. The hadronic matrix elements here that are non-perturbative quantities, so we don't really know how to compute them in general, but they are model independent. So once we have measured them or estimated them with some techniques, we have them for all models. And there is the Wilson coefficients contributions, but if quantities and that are model dependent. So in particular, the BSM dependence lies in the Wilson coefficients. So doing flavor physics BSM is the computation of those quantities. This is why it is crucial to be able to compute them as well. What we do today in automated BSM calculations, so you have here a non-exhaustive list of some codes in this field. So you have user inputs on the left and outputs on the right. You may see, for example, that from a Lagrangian, you can get Feynman rules. And from those rules, you will be able to compute amplitudes and cross-sections up to the one loop level. And you can also derive some Wilson coefficients. So as you see, there is many distinct codes. So many user inputs are necessary with different codes, maybe different conventions. And most of them depend or are written in Mathematica. that is a commercial and closed software for symbolic manipulation. And in particular, if you want a one-loop quantity or Wilson coefficients, you have to have Mathematica. And in principle, if we can get rid of it, we're happy. And actually, it's hard to really automate the calculation of the Wilson coefficients at next to leading order and at one loop. MARTY's principle is the following. So you have one unique code fully written in C++. So you have one unique user input, that is the Lagrangian, the most fundamental description of your BSM model. There is no painful dependency, in particular, no Mathematica here. MARTY has its own embedded C++ symbolic computation library and an application, Graph, that will generate and draw Feynman diagrams automatically. The design in more detail of MARTY is the following. So there is 3 different modules. So MARTY's core that contains the physics with model building utilities, quantum field theory, and group theory implementations. All mathematical computations are done with CSL, and Feynman diagrams are generated with Graph. As output, you will get Feynman rules from the Lagrangian, and you will get Feynman diagrams, amplitudes, cross-sections, and Wilson coefficients. Every calculation is automatic, symbolic, and at the one loop level. And as input now, you can have input files optionally, but you can do everything in a MARTY script. So it's C++ language. And I don't say C++ script simply because you really don't have to know how to code in C++ to use MARTY. It's really just calling interface functions one after the other, and it could be in Python, in Mathematica, in whatever you want. It would be very similar. So now what MARTY can exactly do for you, and first, what BSM models you can actually define with MARTY. So we are for now in a 4-dimensional Minkowski spacetime with spins 0, 1/2, and 1. For the 1/2 spin, there is the Weil, Dirac, and Majorana fermions. And there is also model building utilities, so this is fairly new. So if you don't want to give the full explicit Lagrangian, because it may be very long and complicated with some models, you're not sure of every conventions, you can give a high energy version of the Lagrangian. So for example, here, this toy Higgs sector example, and give MARTY all the prescriptions to break the symmetries, to replace, rotate fields, to diagonalize mass matrices, and make MARTY rederive the final Lagrangian for you. A particle in MARTY can be any irreducible representation of any semi-simple group. So there is not only SUN, but also SON, SPN, and the 5 exceptional algebras for some BSM models. There is a powerful implementation of representation theory in MARTY. And in particular, the algebra generators that appear in amplitudes and that must be simplified are taken into account automatically, including traces of those generators. Now the calculations you can do. So I repeat here, everything is symbolic and automatic. So it means in particular that the user will not have to do anything at the middle of the calculation. MARTY can handle up to 5 external particles at the one loop level, and will give you amplitudes, Partonic cross-sections, and Wilson coefficients. Feynman diagrams are generated automatically, so you can see here an example of a MARTY diagram. And in the main simplifications done by MARTY, there is a contraction of indices as far as possible, Dirac and group algebra, including traces, tensor reduction for momentum integrals. The equation of motions are applied if the particles are unshell, in particular the Dirac equation. Results may be decomposed on an operator basis. So this is typically what you want to do when computing Wilson coefficients. And the definition of abbreviations is also automated. So once you get symbolic results for an amplitude, a cross-section, what you actually want is to get numbers to do real phenomenology, compute observables, plot some quantities. And so For that, MARTY will generate C++ code, so that are C++ libraries. So you give MARTY a mathematical expression. So here C7, a Wilson coefficient, for example, and a function name. And it will generate something like that. So a C++ function taking as parameters every symbols that it didn't know at the moment of the evaluation. And you can use this function then to plot your quantities as the function of those parameters. It's very simple, either from C++ or directly from Python, depending on what you want to do next with those functions. Let's see now a one-loop Wilson coefficient example, an actual calculation I've done with MARTY. So it's the case of C7 and C8 at the leading order. So it's the coefficients of magnetic operators for the B2S gamma and B2S gluon transition amplitudes. So it's 0 at 3 levels, so the leading order is at one loop. We consider only the top quark contributions, and you get here 3 examples of contributions with the W and Goldstone bosons. In the standard model, so the evaluation is done at the energy scale of MW. I've done the calculation in multiple gauges, so unitary and Feynman gauge. It lasts approximately 1 second. The C++ library is generated automatically, and I plot the results with Python. And as a comparison, I've taken analytical formulas from the SuperISO manual. So you can see here on the right, C7 and C8 at the bottom, plotted as a function of the top quark mass. With each time the result of MARTY in blue and theoretical values in red, and you can see a perfect match between the two. MARTY is written for BSM, so let's do some BSM physics and study the 2 Higgs doublet model of type 4. You get charge Higgs contributions like this one here that depend on the mass of the charge Higgs and tangent beta, that is the angle between the 2 vacuum expectation values of the 2 Higgs doublet. Again, analytical formulas are taken from the SuperISO manual, and you can see here the results. So you have C7 plotted as a function of MH plus and tangent beta for a MARTY on the left and theoretical values on the right. And you can see again a perfect match between the two that completes the proof that indeed MARTY can do one loop calculations, and in this case, a Wilson coefficient. Now more practical details for the users. So MARTY is a big code. It's more than 100,000 lines of C++. And to help you start with MARTY, use it and learn it, there is first a comprehensive documentation. So it's HTML format. It's detailed descriptions of everything with many links between functions and objects. And so it's very interactive and practical. And there is also more traditional manuals. So the CSL manual for symbolic manipulations, you should not need it because in the standard use, you should not have to modify MARTY's output. But if one day you want to, you can, because you have all this library to help you. There is also the physics manual. And I would like to stress here a point is that there is many examples in both manuals. And in particular, in the physics one, you have many models from a simple scalar theory up to the MSSM, with each time sample codes that show how to build the model, how to modify it, and how to do calculations in it. So really, it's really simple to start from those examples. The website is under construction.
Grégoire, yeah. Well, 3 minutes left. Sorry, I forgot to go.
Okay, no problem. The website is under construction. So at this address, you can actually get to it. Nothing is uploaded yet. Not documentation manual. MARTY has not been released. The only thing you can get is the slides of today and our contacts if you want to contact us. The status and perspectives. So as you may have noticed, what I presented here is a leading order one loop computation. So there is no tree level contribution, but there is no renormalization in that. in order to have LO computations, you have to have implemented all simplifications, numerical integrals that are taken from loop tools. And actually, you have all the building blocks to go to the next to leading order when the leading order is the tree level. And what will be implemented in MARTY will be renormalization of masses, couplings, fields, renormalization group equations, and that is also fairly new, operator mixing and RG improved perturbation theory for Wilson coefficients. And to conclude, I would like to say first what makes MARTY unique. So you have all theoretical tools in one, from the symbolic calculations up to really quantum field theory, one loop quantities. It's very powerful. So you have one loop calculations, fully automated, amplitudes, cross sections, and in the next future, there will be also the full NLO automated Wilson coefficients that actually does not really exist elsewhere. And we are independent of Mathematica and in general of any other software. That is a very powerful feature. And I will let you on this cartoon here that presents some examples of what observables you can actually compute from MARTY's outputs. So there are theoretical quantities, but that allow to have some real observables like B to XS gamma, that is a highly constrained branching ratio experimentally, so it's really important to be able to calculate it. You can get some flavor anomalies from C9, or maybe lepton physics or dark matter physics. So really, there is plenty of applications possible. Thank you for your attention.
Thank you, Grégoire, for this very nice talk and a very nice tool, I must say. Yeah, I see already a couple of raised hands. I see Chiara, please. Go ahead.
Yes. Yes, hello. So it was really interesting, and I wanted to understand the resources that that are needed for these calculations. You mentioned one example with 1 second, if I understood correctly. I guess that it spans over the different processes that you can calculate and so on. But can you give an order of magnitude of the most used features?
So everything is running on one CPU only each time. It really depends on the calculation you want to do. In particular, it will depend on the number of external legs. So for 3 external legs here, it's really quick. And for a more complicated calculations, you can maybe have several minutes. But I'm actually now optimizing the code for calculations, so I cannot really tell you a final typical time of execution because it really depends on the calculation and it will change in the very near future.
It is very impressive, I think. So, yeah.
Thank you.
Okay, James?
Yeah, so thanks for the presentation. I agree, it is very impressive. So I wanted to ask a more organizational kind of question. So you say this is going to be released in October, but in the long term, do you kind of see this becoming like a community software where theorists from everywhere can make contributions to the code, or do you sort of see some kind of collaboration being constructed? Or I just wonder how you sort of see the long-term outlook for how this will work. Absolutely.
So yeah, the best case scenario, in fact, would be, it will depend on contributors, but a community code that could be handled either by a collaboration or maybe more people would be, is the purpose of MARTY. I'm actually I'm a PhD student, so it will really depend on who will be interested in that and what I will be doing next. And I would like to maybe link MARTY with other codes, maybe in the phenomenological part. To have a really nice code that does many things.
Yeah, thank you very much. I mean, I think the independence from Mathematica will make this a very popular or very attractive tool, I think. Yeah, thank you very much.
I hope. Thank you.
So if there are no other questions, I would make one. I mean, as I said, I mean, this is a very interesting tool. As an experimentalist working on flavor physics, I'm really curious to see what you can say regarding flavor anomaly and then the comparison with the already existing literature. Do you plan to do this? And then the other comment is there are also these flavor anomalies in three level processes, like the semi-tawonic decays. So where you have to calculate form factors and all this. I mean, do you also foresee how do you handle this form factor calculation? I mean, do you accept this as an external input, or do you have any machinery to calculate them?
So now, actually, MARTY is written for perturbative calculations only, because it's really the one you can automate. For the form factors or the hadronic matrix element, in general, this either I will link MARTY with a code that does put things together, but MARTY will probably not derive form factors itself. And in terms of, for the first part of the question, for the physics we could do with MARTY, yes, it's, I will certainly do some BSM studies, real BSM studies myself with MARTY in the next year.
Okay. Thanks. Nazila, you wanted to comment on this? We cannot hear you, I'm afraid. You seem to be unmuted, but if you're trying to speak, I cannot hear you. Well, at least I can't. I don't know if others can hear her.
Now, can you hear me?
Yeah, very well, thanks.
Okay, okay, sorry for the problem. Yes, I just wanted to comment on the calculations of form factors. I think this is really a full another story requiring lattice calculations and a huge, completely different machinery. So yeah, I don't see how you could include all those into the framework of MARTY.
Yeah, but you can take them as input, I guess, no?
Yes, yes. That could be taken as input, but not calculated by the code.
Yeah, yeah, sure, sure. Yeah, yeah. Oh, okay. All right, very well. If there are no questions, no further comments, I say that we would break for, well, as we are quite on time, we are 5 minutes late, so I would resume at 9:20. So thanks, Grégoire, again, and thanks to all the speakers of this first part. And then again, see you in 15 minutes. And please profit from the break by asking questions on the Mattermost channels, if any. Talk to you later then. So I think we can start again with the second part. Can people hear me?
Yes.
Okay, good. So the first talk is on fast entropy coding for ALICE Run 3. And the speaker is Lettrich from Munich. Michael. Yeah, okay. Whenever you like.
Yeah, so good morning and especially a dobre rano to Prague. Yeah, my name is Michael Lettrich and I'm the third speaker today on behalf of the ALICE collaboration. And I will be presenting entropy coding for ALICE data compression in Run 3. And what I'm going, I'm going to outline my talk. Sorry, as this. After a short introduction, I will talk to you about how the data we are trying to compress looks like. Then I'm going to give a brief outline on how we process it, which type of entropy coder we use, and what kind of extensions we needed to do such that it works for best for our data. And I will end with with the current state and give an outlook of what needs to be done and what we expect in the future. So, as my colleagues Chiara and Matteo already mentioned, ALICE is a large heavy ion collider experiment at CERN, with the goal to study the properties of strongly interacting matter at extreme energy densities. And for that, it was equipped with precision tracking equipment, which is able to really swallow so high multiplicities of data. And currently we are undergoing a very big upgrade. Starting LHC Run 3, we are going to record data in a 50 kilohertz continuous readout scheme. This will flood our compute systems with about 3.5 terabytes of data, of raw data from the detector, which during data recording we will have to decrease to 100 gigabytes, so a factor of 35 in data reduction, before parking it in a disk buffer and finishing processing after the let run is over. And where the entropy coding then takes place is the last step in the online processing, where we try to decrease the data rate even more. So the objective specified in the technical design report is that it should be possible to losslessly compress the data by around a factor of 3 within 35 seconds using an entropy coder. And so this is the framework we are challenged by. So in a nutshell, what do we do with an entropy coder? So an entropy coder tries to find the most efficient representation of the source data, of the source message, based on the statistics of the message. So more frequent symbols get a shorter representation, less frequent symbols get a longer representation. So the symbol C, which occurs only one time, will get a longer code than A, which occurs, for example, 3 times. And this way we are able to squeeze down the data rate. And there is a physical limit, though, to which you can go, which is the entropy. And so this is like the speed of light. It is like you cannot go below. There is this is the limit for us. So what does the data look like that we're trying to compress? So the data is being processed in the synchronous stage in so-called time frames. So we get around 10 to 20 milliseconds of data, and this is dominated definitely by the time projection chamber, contributing over 90% of the data to be compressed. And then each of the subdetectors provides its own flat array, flat structure of arrays of data that needs to be compressed, and that needs to be merged compressed and merged into the actual complete data frame, or the time frame, compressed time frame. And the data itself is quite big, so we get up to 25 bits per value, which means that there is up to 2 to the power of 25 possible symbols that we need to encode. And we need to be the encoder needs to deal with, and the symbol distributions are sparse and clustered. So you can see that we have a lot of out of 2 to the power of 16 possible values. In this case, only less than 400 values were actually taken, and the rest of the values simply didn't occur. And the distribution of this data stays more or less static over multiple time frames, so there is not many big changes here. And there's a special requirement that sometimes the data will have repeating symbols, such as in flag fields. So, for example, we will have the multiple symbols occurring a couple of times after another. So this is something we should be able to exploit as well. So how are we approaching this? So each of the subdetectors will be encoded separately, or is responsible for its encoding separately. We have individual treatment of each flat array in the structure, dealing because each of them has a specific symbol distribution, and this way we can achieve a very good the best possible compression factor, and each of the arrays can be processed independently in parallel. And additionally, of course, we can tweak and tune the structure of to the structure of the array and really achieve the best possible compression. The data, as I said, is being compressed and encoded by each subdetector individually, and then the actual compressed time frame, which is written to storage, is being assembled from that. And the encoder we used for that is the so-called asymmetric numeral systems encoder, and the variation of that, which is a fairly recent, but very, very efficient type of entropy coder. And what it does, it looks again at the distribution of our source symbols, and based on that, it encodes all the symbols from the message into a single integer state with x. So, for example, if we take this message here, its encoding will be the number 459. And after decoding, this number suddenly then becomes again this message. The ANS coder uses arithmetic operations to do that, and basically it grows the state here, the state x grows inversely proportional to the symbol probability. So again, a more frequent symbol, like for example, like the symbol A here, will grow the state less than the encoding of a less frequent symbol C. So here we have a growth in factor 2. Here we have a growth in roughly factor 6. And also the decoder of this, the decoder works exactly inverse to the encoder. So given a state, let's say 77, the decoder will be able to say, okay, the last symbol encoded was symbol C, and it will spit out the state 12, so for which the next decoding step can be produced. So within our studies, RANS has been a very high performance encoder.
Michael, 5 minutes left.
Yeah. We have a very high performance encoder. RANS compresses almost down to entropy, so to the physical barrier of what is possible without altering the information content in our example, and does so at very high bandwidths. It did so for all the data we have been throwing at it. And that's why we chose it really as the backbone for the compression in Alice Run 3. However, there is a couple of things which we needed to do in addition to make sure that that it's up for the data we have. So we needed to ensure that these large set of values that we need to process, so this up to the 2 to the 25 possible values can be processed. Then then we need to deal with these sparse symbol distributions and exploit the fact that our source symbols stay static across timeframes. So yeah, and deal with the repeating symbols. This is were all additions that we had to add. For the sparse alphabets, we needed to optimize the storage of large alphabets, simply because we have because the alphabets were sparse, and we could bring down the memory consumption significantly by a more efficient storage scheme. Then we introduced, in addition, we exploited in addition the fact that the symbol distributions stay static over different time frames, so we can actually we don't have to do for every time frame. We don't need to process again and again the symbol statistics and hope that nothing changes. And but for that we actually had to additionally implement the treatment of so-called rare symbols, so symbols which in our symbol distribution do not appear and would produce an error in the encoder. We had to make sure that these get properly recognized by the encoder and nevertheless encoded such that they can be recovered correctly, even if we lose a bit of performance. And in addition, we introduced the space-efficient treatment of duplicates, so that we get rid of duplicates, such as, for example, this 4 Cs in here, by making sure that the deduplication algorithm is actually aware of the fact that it's being run in a in the ANS encoder, and we only deduplicate if we see that we benefit from it, so that the data size goes down. Currently, we have the core RANS implementation with our adaptations ready, which can be configured according to the needs of the source data, and integrated most of the subdetectors into the scheme. However, there is still the integration of the remaining detectors, which is pending. The data format is not completely done yet, and the static distributions need to be integrated better into the system by means of coordination and conditioning and calibration database, and generally just performance tuning and integration of components. Otherwise, I can say that RANS is a fast and efficient entropy coder, which can really deal well with the requirements for Alice Run 3. I would like to thank you for your attention and ask for questions.
Thanks, Michael, for this interesting presentation. So I would open the floor for questions and comments, if any.
Maybe I could ask a question if there's.
Yeah. Go ahead, please.
So I was wondering, Kyle, if how these entropy encoders compare with, you know, like the standard encoders that we tend to use in offline software, you know, the kind of zip encoders, LZ type of things. Are they way more efficient than that?
Let's say the thing which, in the end, zip, for example, is in the end or Z standard is a mix of an entropy coder and a special dictionary methods, but they are not they're not aware of what they're encoding. So they simply chunk up the data in 8-bit chunks, build the statistics over them, or even have pre-saved statistics on how often these should occur, and then they encode. So basically, the better you approximate the underlying probabilities of the symbols you're trying to encode, the more efficient your encoding will be. So this is where we definitely where we can outperform these classical encoders by really factors of 2 or 3. And then also these rely heavily on dictionary methods. So they try to find patterns of reoccurring symbols and merge them together, which is very compute intensive and is simply not, it simply doesn't yield any benefit for what we do. So this is why we actually went in and implemented all these things from scratch by ourselves, because the things used in industry simply don't cut it.
Perfect. Thanks for the explanation.
I have a small question regarding your slide 13. When you mentioned that you only use for 139 values out of 2 to the 16th, and then you mentioned that how you treat possible outliers. I mean, so how do you do this in practice? I mean, I didn't get how.
Yeah, it's a bit of a complicated process. So, but in the end, what we do is we introduce a so-called functional character for all the symbols which are outliers. And instead of encoding the symbol itself, we encode this functional character and have sort of and add a stack, more or less, where we just put the raw data. And during decoding, when the decoder finds this functional character in the stream, it will look up the symbol and put it back in place, so that we can deal with these outliers without sacrificing compression performance or encoding performance.
Okay, yeah, great. That's very nice. Any other comments or questions? So if not, I would thank Michael again and move to Matt Barrett, who will tell us about the Belle II RAW data management and the online-offline data transfer system.
Okay, thank you. I'll just start sharing my screen now.
Yeah, sure.
Okay, so hopefully you can see now. So yeah, I will talk about raw data management at Belle II and the systems we have developed thus far for this. So there's an outline here while I'll talk about the experiment, the data flow, and the evolution of our system and some operation and monitoring information. So the Belle II experiment, as many of you will be aware, is an experiment in Japan, in Tsukuba near Tokyo, the successor to the Belle experiment. And we started our first physics run in March of 2019. And the Belle collaboration now consists of a little over 1,000 members from all around the world. So the goal of the Belle II experiment is to collect a data set of 50 inverse attobahns. So that's roughly 50 times the size of the data set for Belle, to hopefully discover new physics. And 50 inverse attobahns of data will correspond roughly to 60 petabytes of data in total. And the rate at which we will be collecting data will increase over the data-taking lifetime of the experiment. So in the later years of the experiment, the instantaneous luminosity will be of order 100 times what it was when we started with our first run in 2019. And so you can see in the plot here how the instantaneous and integrated luminosities will increase. And if you are interested in more details of the Belle II program and how it will develop, then you can see the talk by Kodai Matsuoka later today. And I'll also point out that Belle II did set a new world record for instantaneous luminosity back in June of this year. So moving on to the actual data flow of Belle II. So our online system, our data are recorded by the Belle II data acquisition system, and then stored on servers which are located close to the detector. They are written in a format which we call SRoot, standing for sequential root. So this allows for the serialized writing of the data, and it doesn't involve any compression. So moving on to the offline system, the data in the form of the SRoot files are transferred via a dedicated connection to the KEK computing center, and that's located just over 1 kilometer away from the detector. And in order to use the files for physics analysis, they have to be converted to root format, which, as you're probably aware, is compressed. And we have a number of front-end servers at KEK Computing Center, which are used to convert the data to root. And then the raw data are copied to permanent storage, and we have a policy that there must be at least 2 copies of every file. So now I'm going to go into a little bit more detail about the implementation we had in early 2019 when we started our first physics run. So the DAQ system created a list_send file, which, as the name suggests, is a list of files, a list of the SRoot files to be specific, that are ready to be copied away from the online system. And so the list_send file was copied to the front-end servers, and then the transfer of the SRoot files to the servers was started. And following that, the SRoot files were converted to root. And then finally, the files were archived, and there were tests such as the verification that a number of events matched. And you can see here how all of these steps were done in a sequential manner. So once all of that was finished, the data was made available to the collaboration, specifically our data production group, which prepared the data for physics analysis. So during this time, many of the steps were initiated manually. So a member of our computing team would perform these tasks. And this was very useful in helping to detect anomalies and debug the system, but such a manual system simply would not scale to the higher data rates we expect, and it would be a lot of effort for one or a small number of people to maintain such a manual system. So we needed to adopt an automated system, and sequential processing also underutilized the computing resources which we had. So the bottleneck was the SRoot to root conversion, and only about 25% of the available CPU was ever used during our processing times. So from mid-2019, we moved to an automated implementation where we have a system automatically searching for new listsen files, and the automated system spools them, initiates transfers of the SRoot files, and puts everything into a queue system which uses task spooler. Whilst we still have files to transfer, then the queue system is split between transfers and conversions. But once the transfers are finished, then we dedicate all the resources to conversion. So our CPU utilization improved to about 85% using this system. And so the system also does the copying to permanent storage, and assuming that the quality checks are passed, then the release to the collaboration follows. Moving forward now, so we've had this system since mid-2019, and we've continued to develop it. So for our 2020 run, which lasted from February or March of this year up until earlier this month, we have on a number of days produced 50 terabytes of data, or even slightly more. That's the combined total for both SRoot and root files. And the root files were typically about 45% of the size of the SRoot files, the root files. Keeping the SRoot files has been very useful for understanding and debugging the early data, but keeping two forms of the raw data around is not something we plan to do in the long term. So we will not be storing the SRoot files indefinitely. We will delete them in due course. So root will be the only form of the raw data which we do store long term. So as of this month, we have recorded over 1 petabyte of data in root format. Most of the runs, most of the data are from physics runs. We also have beam studies, some global cosmic runs, and also some which are just used for debugging purposes. So you can see the data size for our 3 runs we've had so far, and our string run this year has been by far the largest run in terms of luminosity and data size. As I mentioned, our luminosity will increase a lot for future runs, and at the moment we are basically writing out everything that reaches the high-level trigger, but we will apply filtering of events at that level, which will reduce the data size by about 9 times. So for future runs, the data volume per unit of luminosity will decrease markedly. And it's also worth mentioning at this point that the maximum rate our DAQ system can write out is about 1.8 gigabytes per second. And we have tested our system and we've seen that we can cope with over 2 gigabytes per second. So our system should cope with the higher luminosities even if our DAQ system reaches its maximum rate.
5 minutes, Mark.
Okay, thank you. So in terms of the turnaround time, which we define as the time from when a run ends until the root files have been archived and are in principle available to the collaboration, generally that's about 5 to 10 hours. But you can see that there is some variation depending on various factors, which is generally quite reasonable, but there are times when some of our subdetector experts do need the data available faster. For example, when we're doing studies with changing detector conditions or accelerator conditions. So we have created a fast lane which will allow the experts for each subdetector to request the data faster. And so for short runs, the files may be available on our central computer system within about 10 minutes of the request being made. So coming back to something I mentioned earlier, the permanent storage of the data. So we utilize the grid for our distributed data analysis and also for moving our raw data around. And so we use Dirac and an extension of that called Belle RAW Dirac to distribute the raw data. So there is a link there if you're interested in learning more about that. And of our 2 permanent copies, we have one at KEK and the second is at Brookhaven National Lab, BNL, in the US. From the 4th year of our data taking operations, that second copy will be split between BNL and sites in Italy, Germany, Canada and France. We've been developing an automated system to transfer the data to BNL using Dirac and Belle RAW Dirac during the Spring 2020 run. So you can see on the graph here, the blue is the data in root, raw data root format at KEK, and the red is the data at BNL. And you can see it's mostly kept up. There have been a few periods where we have been doing development work to improve the automation of the system. And you can see those periods in the graph there, as well as the fact that the system has the capability to catch up when we do have delays for development work. Final topic I just want to mention is control room monitoring. So if there are delays in our data flow system, that has the potential to reveal issues on the online side, and also at towards the end of the experience data taking lifetime, when we're running at much higher luminosities, if there are delays in the data flow, they have the potential to cause delays in actual data taking when we're at much higher luminosities. So we've added a monitoring screen into the Belle II control room, so our control room shifters can see what the situation is with the transfer of the data and the data flow, and the shifters and experts can look at alarms and see what the situation of the system is, and if anything needs to be done or communicated with the data acquisition team, for example. So in summarizing, we're a particle physics experiment. We started taking data just last year. And we expect that the rate we will be taking data out instantaneous luminosity will increase greatly compared with what we saw in our first run. So we've been implementing an automated data transfer system to transfer the data from the detector to permanent storage, and we've been making sure that the system will scale to the higher rates expected during the later years. And it's also worth noting that the hardware which we have at the KEK Computing Center is replaced every 4 years, ensuring that the new system we get each time will meet the needs of the experiment. Performance monitoring and making information easily accessible to other members of the collaboration have also been key in designing the new system. And the system has been operating in production since June of last year and has performed quite robustly. And we have submitted a journal paper describing the system and going into many details of the operations. So thank you very much for listening.
Okay, thanks, Matt, for this nice talk. Let's see if there are any questions. I see Chiara.
Yes, may I?
Sure.
Okay, so thank you very much for this interesting talk indeed. So I wanted to ask 2 questions if possible. So you discussed that from the very first data taken, you have this increase in the CPU usage from 25 to 85%. So I wanted to understand whether it is only because it is more automated or if there's something else, because in principle, I would have expected that the processing of the data is the same, it's just more automated. And the second question is, in what will consist this HLT reduction or compression? If you can elaborate a bit.
Yes, sure. So the increase in utilization is because before in the sequential processing scheme, we were basically waiting for each step to finish before the next step started. And the conversion of the sroot files to root files did take a very long time. So being able to have other things, the transfers take place in parallel with that was the main factor in increasing the CPU utilization, which was very low before. So I hope that answered your first question. So moving on to the HLT filtering. Unlike the LHC experiments, the rates we see at Belle II are much lower. So in principle, our HLT can basically write out every event which reaches that level at our current luminosities. Basically, it means that the HLT will start rejecting events which won't be written in common with the triggers at most HEP experiments.
But will it be based on a sort of event type selection, or I don't know, noise events, or how do you decide whether to reject or not an event?
Yes, so it will be based on event categories and certain classifications of common event will I think start to be pre-scaled, for example. But I don't know the exact details, but that's the general design.
Okay, thank you very much.
Any other questions or comments? I'm curious to know about how do you do the bookkeeping of all this data? I mean, it's a bit out of scope with respect to your talk, but what do you use?
Yes, so we have a MySQL database in which we record the information on every file which is written by the detector. So on this slide, you can see in the top right-hand corner box there, we have a box total files there. So our since we implemented our automated system, we have a nearly 1 million files with their information stored in that database.
Okay, and then you integrate this within your Dirac instance, or is independent?
So this database is independent of Dirac, but then we do have Belle RAW Dirac, where every file is registered with in our Dirac system.
Okay, great, thanks a lot. So if there are no further comments or questions, I would say that we reached our second break. So we will have another coffee, or we can steer our legs maybe and come back in at 20 past 10, right? So talk to you later. Okay, I guess we can start again. Now, the first of the final 3 talks of this session will be given by Chieh from Taiwan, who will present the data acquisition system of the KOTO experiment. So please, Lin.
Yeah, thank you. Yeah, so I will talk about the KOTO DAQ in this presentation. Okay, so first of all, the KOTO experiments aims to research the real count decay, K-long decay into Python bar, which is highly suppressed in the synthetic model because of the small theoretical uncertainty. So it is also very sensitive to new physics. So the principle to study the real decay, K-long decay into Python bars, we have 3 items. First one is that we require 2 photons hitting CSI, which are from pion. And also we require that this pion should have the missing transverse momentum because of the neutrinos. And the third requirement is that there's nothing else detected in surroundings. Otherwise, it might come from the backgrounds. So based on these principles, we design our triggers based on some features. So the level 1 trigger, first of all, is the ET and the combination of ET and veto. So the ET here is the energy sum in the calorimeter, as we see here, because there are 2 photons enters the CSI calorimeter. And also the veto, as I mentioned, that there should be no any hits in the veto counters. So we require that the order of veto signals should be 0. And these two signals combination will be the level 1 trigger. And if it is fulfilled, then we will have the process the level 2 trigger, which is based on the number of clusters. So we can see here, we will count how many hits we have in the CSI calorimeter. If it's also fulfilled, then we will save these events. And this is the basic strategy of our KOTO DAQ. The fundamental of the KOTO DAQ is realized by the pipeline readout. So we have pulses from nearly 4,000 channels, and we will continuously digitize the pulses at 125 megahertz sampling frequency. The pipeline depth of our ADC is 5.2 microseconds. So it means that we need to decide to keep these events or not within this 5.2 microseconds. So first, we will do the feature extraction to extract the information we want and send the results to the trigger core. And this trigger core will also receive other the features from other channels and do the analysis and decide to collect these events or not. If the answer is yes, then we will issue a trigger to all of the ADCs. Once ADC receives the trigger, it will take a snapshot and record this event in the PC for the offline analysis. Okay, so from now on, I will start talking about how we extract the features. So for the level 1 trigger, first of all, we have the pulses, and we will calculate the pedestal first and seek the peak. So the peak by definition should be larger than neighbors. So for example, the red circle here, this peak needs to be within the time window. And if it's satisfied, then we will convert the peak height into the energy. So this conversion is driven by the calibration. So it differs channel by channel. For the energy sum, we will do the summation all over the channels. And for the veto, we just do OR for every channel. To realize this summation, we adopt the technique called the daisy chain. So the idea is that, so for example, in this cartoon, the first ADC will do the summation within its board and then send the energy sum to the next board, the second board. The second board will do the same thing, do the summation within its this board and add the previous one and sends the final results, ET1 plus ET2, to the third board. The third board will just repeat the routine and so on and so forth until it's received the summation board. The summation board will have received lots of local ETs and do a summation again, sends the global ET to the trigger center. The trigger center will judge this is the event we want or not and issue a trigger. So that's the strategy of the level 1 trigger. If level 1 trigger is satisfied, then we will have the level 2 trigger processing. The level 2 trigger is based on the number of clusters. So here is the event display. We can see this is the calorimeter, which is made of CSI array. In this event, we have 6 photon hits, and we will convert this map into the bits. So this is the bit map in the DAQ system. The algorithm to count how many clusters we have is based on how many turns we have in this map. So let me take an example here. So imagine that's your person walking along this contour. So as we can see in this diagram, we will make 5 clockwise turns and 1 counterclockwise turn. So the difference will be 4. 4 means 1 cluster. So by doing these calculations and divided by 4, we will know how many clusters we have. And this algorithm can be processed in a very high speed. So it has a very good reduction on the deck time. In our measurements, it's 0.16 microseconds. Okay, so let me talk about the DAQ performance. So first of all, is the trigger rate reduction in June 2018. So first of all, the raw triggers, at the very first beginning, if we only trigger based on ET only, that would be 480,000 triggers per spill. And after the level 1 triggers, it becomes 22K per spill, which is a large reduction through the level 1 triggers. And if we further impose the level 2 triggers, that would be 13K per spill. So we can see how the trigger rate changes. And this plot shows the DQ lifetime ratio, which means how many triggers can be correctly processed and saved in the PC. And at the end of 2015, the life ratio is about 80%. After this final upgrading, we can see in the end it's 99% of the life ratio, thanks for the large improvement in the dead time. Okay, so in this page, I will talk about the level 1 trigger performance. So to study the efficiency, in the offline analysis, we will check what is the online effects here. And after the analysis, we got this efficiency curve. So the left plot is the ET, which is from the calorimeter. And the green dashed line means the offline threshold. So as we can see, this is the turning point, and the cuts we set at 500 MeV. So this cut value is far from the threshold. If we fit this curve by the error function, then it's about 3 sigma away. So it's a safe self trigger here. And the right figure shows the veto. The offline threshold is 100 kV, and the turning point is also 3 sigma away. Overall, the level 1 trigger efficiency, we arrive at 99%. And in this page, I talk about the level 2 trigger performance. So the level 2 trigger efficiency is studied by the Monte Carlo. So the Monte Carlo, we simulate the waveforms and apply the exact same algorithm on these Monte Carlo files to see what's the efficiency from the online clustering. And to have the cross-check, we also process the similar thing as on the data. So the data, the online clustering will be in the tagging mode, meaning we will just record the online cluster results without selection. And we have 2 modes here. One is the k-log decay 2 pi 0, another one is the k-log decay 2 gamma. 2 pi 0 gives us 4 clusters in CSI, and k-log decay 2 gamma gives us 2 photons in CSI. So these 2 modes help us to confirm the reproducibility of this Monte Carlo driven method. And if we see the efficiency is similar, so it gives us the confidence of this method. And the ultimate goal is to collect the Python bar events. So based on the Monte Carlo results, it's 99.6% of the efficiency on the level 2 trigger. Level 2 trigger.
So 5 minutes left.
Thank you. Okay, and page 12, I will talk about the future plan about the level 3 trigger construction. So in the near future, we will have the level 3 trigger, which is based on the PC farm. Currently, we basically collect the Python bar events, but we can also collect the byproducts like Pi0 E plus E minus, which is physics motivated. But currently, it's hard to collect the data, this data by the current level 1 and level 2 triggers. So in order to have this data collected, we have the new architecture of the our DAQ. So we will make the event building modules before entering the PC farm. These event building modules will have the complete events in the end. And from this module to the PC farm, we will use a 10 Gbps transmission speed to the PC farm and make a complicated, sophisticated trigger decision. And I think we believe in this strategy, we can also be able to collect the byproducts. Okay, so this is the conclusion. So based on this latest performance of the KOTO trigger system, the lifetime ratio is 99%, and also the trigger efficiencies for both level 1 and level 2 triggers are 99% for both. And the trigger rates is 13K per spill. And we'll also have the level 3 trigger in the near future to broaden KOTO's research territory. Thank you very much.
Thanks to you. This is for the very interesting talk and the challenging topic of an experiment where nothing comes in and nothing goes out.
Yeah, thank you.
See if there are any questions to Lynn. I have a small question on your slide 10. I see that you show in the left plot the online trigger efficiency. So I wonder how this is defined, because I see some points well above 1, just close to the threshold to the turn on point, right?
Yeah. So for the ET triggers, we directly fit with the exponential function. And so this efficiency is defined by the major data points to the fitting results.
Mm-hmm.
So it's possible that these data points is larger than the fitting points.
Ah, okay.
Yeah.
Yeah, and also there is a, I see, okay, see what you mean.
Yeah.
Okay. Any other comments? Okay, if not, thanks again. And
thank you very much.
We can move to the next one. Muhammad and CERN will mention talk about the migration of CMSWEB cluster at CERN to Kubernetes.
Hi, can you hear me?
Hi, yeah.
Okay. So I'm sharing the slides. Can you see my slides?
Yes, we can. Full screen, perfect.
Okay. So in this talk, I will describe about our work that we perform regarding migration of the CMSWEB cluster from the virtual machine clusters to the Kubernetes technology. This is agenda of the talk. So I'll start briefly with the introduction and the motivation behind this work. And then later on, I will describe the current architecture of the current cluster, which is running on the virtual machines. Then later on, I will describe the proposed architecture of CMSWEB in the Kubernetes technology with various perspectives such as service deployment procedures, deployment cycles, how we assign resources, how we do monitoring in the CMSWEB for Kubernetes, what issues we face during this migration, and what lessons we learned during this whole process. And later on, I will describe how we perform the performance analysis of both cluster, and then I'll conclude with the future work. So as we know, CMS experiment runs hundreds of thousands of jobs on the daily basis. So we have a dedicated cluster, which we call as a CMS web cluster, which is used to host various CMS essential central services, which are responsible for various tasks such as data management, discovery, and data bookkeeping, etc. So this CMS web cluster is currently running on the virtual machines, which is deployed on the CERN OpenStack cloud infrastructure. And each service is managed by its own development team. For example, there are various groups: WM Core, DBS, CRAB, and DAS, etc., TQM. So these various groups run their services on the CMS web infrastructure. So due to the complexity of heterogeneous environments and different schedules of these development teams, we only support monthly release cycles at the moment. So each upgrade cycle include the building of RPMs from the source code. We perform the cross validation and the interaction of all the services in the testbed environment. Once everything is validated, then we perform the migration to the production environment. This whole procedure during the testbed requires a lot of interactions between development teams and the CMS web operator. And we also need, there is a lot of manual interventions by the CMS web operator to manage those clusters and services. So it means that the production releases are only deployed once a month. So if a developer has anything ready to deploy in the production, so it means it had to wait 4 weeks before their new version of their services is deployed into the production. And this is because the production upgrade incurs downtime of services, and the services requires proper validation and interaction of services before the services are going into the production. So due to these restrictions, we only perform production upgrade once in a month. So to enhance the sustainability and the issues of this current release cycle, CMS decided to adopt a containerized solution, which is based on the Docker and managed with the Kubernetes. So with the containerized approach, developers will not have to ask every time the CMS web operators to deploy the new version of their services. In fact, they can be able to deploy the services in a few seconds, and it will significantly reduce the upgrade cycle, the end-to-end procedures, and the operational cost as well. architecture of the current virtual machine cluster of the CMSWEB. So we have Apache front ends which accept requests from the users. This Apache front ends provide the CMS authentication on the basis of X509 certificates. And after the users are authenticated, these Apache front ends has the proper redirection rules to forward the request to appropriate services which are running on the various virtual machines. So these backend services only accept the request from the front end services. So this provide like additional layer of security that the users cannot access their services directly. So in the proposed architecture of CMSWEB, the users interact the index controllers that provide additional layer of transport level security, and then the requests are forwarded to the Apache front end, which similarly to the VM cluster provides CMSWEB X509 certificate based authentication. And after those requests, the request is forwarded to another cluster. So in this way, we have two clusters. One is for the front end services and other one is for the back end services. So both run the Nginx ingress controllers, which accept the requests that is coming to the cluster at the first hand, and then forward the request on the base. So in the backend cluster, this Nginx ingress controller also has proper redirection rules to forward the request to the appropriate services in the backend cluster. So in order to deploy procedures for the CMSWEB Kubernetes, we have a repository which here CMSWEB Kubernetes. It has two areas like Docker area and the CMSWEB area. So we need, first of all, we need Docker images, which Docker containers that needs to be deployed in the Kubernetes. So we have the Docker area which contains area for each service. So each service, for example, has 4 different files, kinds of file. We have a Docker file that is used for the specifications to build images. And then we have install script here that is used to install the RPMs for the CMSWEB. And then we have a run script to run the service, and we have a monitor script to control the monitor. So Docker area is used, this area is used for the creation of images. Then we have a CMSWEB area here. Once the images are created and uploaded to the Docker Hub repositories, then those images can be deployed in the Kubernetes using this area. So here we have different directories and different manifest files. So these manifest files are used to deploy those images in the Kubernetes. So further detail is available in the repository. So this diagram shows the service deployment cycle. As we can see, it is a cyclic procedure. So first of all, users update their code in the repositories, and then the RPMs are built on the basis of the code. Once the RPMs are there, we can build the new image and upload it to the Docker Hub. Once those new images are available in the Docker Hub, we can deploy those new images by using manifest files, by properly adjusting those images. So in this way, once there is any new update, so the users will update the specification file and then build RPMs and create image and upload the image, and then we can deploy those images in the Kubernetes. So in this way, this procedure for the Kubernetes as a cyclic procedure continues. So this example shows how we allocate resources in the Kubernetes. For example, we have different services. We run various replicas or instance, or in the Kubernetes, we call them the pod. For example, for the data aggregation services, we run 3 pods, and then we can assign the minimum and maximum value of CPU. Here M represent the millicore. So 2 CPU for the minimum and maximum 4 CPU for each pod can be assigned to this dash service. And then we can get the minimum and maximum total CPUs for all these services. Similarly, we can assign the minimum and maximum RAMs. So in this way, we can assign the resources according to our needs. But this in the virtual machine clusters, we cannot do this. So we allocate these resources on the basis of existing VM-based clusters, and we gradually adjust and tune them on the basis of stress and integration testing in the Kubernetes. So this diagram shows how we perform the monitoring in the Kubernetes. So we have two components. One is called the log stage and other one is for the Prometheus. The log stage is used to collect logs using the file-based daemon that is running for every service. So the logs are sent to the Elasticsearch in the Sun Monit infrastructure, and the Prometheus service is used to collect various metrics and display those results in the Sun Monit infrastructure using Grafana in the form of charts and tables. So we face various issues in this migration. So we categorize those issues into two kinds of issues. One we call them infrastructure issue, and other one is called service issues. So this are some issues we faced during which are related to the infrastructure issue. The major issue from them is the network degradation. I will describe in the next slides, and some of the issues which are related to the services issues. I'm not going into the technical detail, and all these issues have been fixed, and we like to thank the support from the Sun IT we get to fix those issues. So what are the lessons we learned? As we know, the existing virtual machine cluster, it requires a lot of interactions between operators and developers, and we need a manual intervention from operators to deploy and maintain the cluster. But the new Kubernetes infrastructure automates most of the tasks, and it greatly reduces the efforts and the workloads on the operators and the developers as well. It automates the procedure, and it enables developers to deploy services directly in the Kubernetes without needing input from the. So in this way, we can also say that developers will not have to wait for a month before the services can be put into the production, and also we will not there will be no intervention for the services during this deployment procedures. So there is a very strong feature in the Kubernetes which is called the auto scaling, which adjusts the resources dynamically on the basis of the usage. So, but this feature, auto scaling feature, does not exist in the virtual machine clusters. So it means when there is high load in the VM cluster, the services might become less responsive, and there is often manual intervention from the operators to adjust the resource to manually interface and resolve issues with the services. And we also learned that the manifest files in the Kubernetes, it requires a proper verification and proper identification. So in the performance analysis, we use the Hey tool to analyze the performance, and we can say that here there are different services here and the requests per second. So we initially face the issue of the major issue which is related to the network degradation, and as you can see, these small values which is related to the old Kubernetes cluster that has those issues. So this issue was fixed by the Sun IT in collaboration, and this issue was related to the wrong network drivers. So once they update the drivers with the Calico network drivers, this issue was resolved in the new Kubernetes cluster. So as you can see, these are the virtual machine cluster, both in the testbed and the production, and these are the results for the Kubernetes clusters using various replicas of the frontends. So we can see the Kubernetes cluster performs better as compared to the old cluster, and also as compared to those VM cluster for the testbed and the VM for all the services. So in this example, we show how we perform tests. In the second scenario, we put a load on the front ends service, and we can say that here, as we increase the number of replicas, the performance of the Kubernetes cluster increases as compared to the cluster of the virtual machine for the testbed and the VM. So during these various configurations, so we can see that the Kubernetes cluster performs well as compared to the virtual machine cluster, and this is because of the dynamic adjustment of the resources. So in the future work, the default configuration of the Kubernetes performs auto scaling, means they adjust resources on the basis of the CPU and the RAM usage. But we would like to deploy auto scaling facility on the basis of the service metrics we use for the Prometheus. For example, we can auto scale the resources Apache. So for example, we can auto scale Apache server based on the number of incoming requests instead of the CPU and the RAM usage. So we are currently working on this work, and then we would like to work for the on the deployment of service mesh. The service mesh provides plenty of benefits. So major benefit is provides various versions of the same service running at the same time, and we can adjust traffic between those various versions of the release. So Istio and Glue are the two middleware that provide the service mesh deployment. So we are also exploring this in our future work. So in the end, I would like to conclude that the new cluster in the CMS, it enhances the sustainability and it reduces the operational cost of the CMS. So with the containerized approach, developers will not have to wait for the operators to deploy the services, and they not have to wait for a month before the services can be put. In fact, they can be able to deploy the services their own and within a few seconds and without intervention. So it allows CMS that will significantly reduce this monthly release upgrade cycle. It will reduce deployment procedure and operational cost as well. So at the moment, we are running both virtual machine clusters and the Kubernetes clusters in the parallel fashion. So once developers have tested their services initially, and they are performing some of the services require stress tests, which is currently going on. Once everything is finished, then we will run both clusters in the parallel fashion for a few months. Once everything is validated, then we will retire the old clusters and we will move additional cluster. We will move the services to the product Kubernetes cluster only. So that's it. All from my side. Thank you for the attention.
Thanks a lot, Mohammed, and for this nice presentation. James, I see James has a remark to make, please.
Hello, yes. So thanks for the very nice presentation. So can I ask, has this now been deployed for production, or it's still not, the migration hasn't completed yet?
Yes, it has been deployed for the productions, but the services developers are validating their services in the production. Most of the services have performed basic validation, and they are running at the moment the stress tests and integration tests to be performed on the production clusters. So we will run both clusters in the parallel fashion for a few months, and we will use the DNS alias switch mechanism, in which the request will be sometime requests will go to the Kubernetes and sometime requests will go to the VM cluster. So in this way, we will run both clusters at the same time.
Okay, thank you. And are there any limitations that you see to the Kubernetes containerized setup, or you're essentially entirely happy with it?
Well, we face some issues as I said in one slide. So these issues have been fixed. There were various issues, and now at the moment the cluster is running fine. So I'm not going into the technical detail. It's more like we can discuss offline if you want, if you are interested in this issue.
Okay, thank you.
I have a question about the efforts that were required to switch from virtual machines to Kubernetes. I mean, how, in terms of people, I mean, I see that there are five people listed, but I mean, in terms of efforts, how long did it take to implement all this? I mean, how many people were involved? I mean, can you comment on this?
We started this migration process at the end of last year, maybe October or November. We started this work, and currently initially there was Lena, which has left now. So mostly the work is being done by the Valentin and myself. and now we have Andreas Pfeiffer and one more guy as well.
Okay, so this you did in a time scale of 6 months, approximately.
Yeah, you can say like that. Yeah.
Okay.
Well, I have a comment. This is Danilo. It's, I mean, Imran is on this not 100% and is doing an excellent job. Plus, with the help of Valentin Kuznetsov, that is not 100% on this, plus Andreas Pfeiffer, that recently joined. So if you want, just stick to it. 2 FTEs of very experienced administrators with in-depth Linux knowledge. Okay. Just to sum it up, then it really depends on the complexity of the cluster that you want to deploy. I mean, the portfolio of the internal services of CMS, which we call CMSWEB, that it is not, as you could understand from the presentation, web pages or web servers is much more. There is data discovery. There will be Rusio deployed into it, and there is the workflow management also. It's rich. Okay, it's not a small thing. And the fact that you have these auto-expanding resource allocations, it's something that gives CMS the advantage of using very well the resources which are given in this case by CERN, because you don't have to allocate n virtual machines just in case and then underutilize them.
Yeah. No, I mean, this is very interesting also because in terms of automation, it's much streamlined. I mean, I understand that the activity is much more streamlined with respect to the past. Okay, so thanks. Yeah, of course, I mean, I have a personal interest in this for other reasons. So, all right. Thanks a lot. If there are no further questions or comments, I would thank Muhammad Imran again for his presentation. And we move to the last talk of this session on VegasFlow, accelerating Monte Carlo simulation across platform with dataflow graphs by Juan Manuel Cruz Martínez from University of Milano.
Hello. Let's see. Can you see my slides?
Yes.
Perfect. Okay. Hello, everyone. So I will be talking about VegasFlow, which is a Monte Carlo library for integration using GPUs and CPUs based on TensorFlow. So I will first motivate the need for such a library using my own background, which is high energy physics, in particular proton simulation, and then I will comment about what is VegasFlow and show some benchmarks. So some of you surely have seen this integral before, but basically most of the results that we theorists produced has to do with this integral. These represent a proton collision where the Parton distribution function contains the physics of the initial state, the matrix element, the physics of the collision, and the jet function I'm using to represent the fiducial phase space that we are integrating over. So basically, in an schematic way, these are the ingredients that you need to produce in order to generate results. So you need an integrator, obviously, that you give the integrand and it gives you a result, and then you have to build this integrand. First, you need to generate the phase space, apply the necessary cuts, define the physics of the collision, and then you might have some histogramming or analysis tools that produce the results you're interested in. And these are in general very expensive calculations in terms of CPU. And so I was looking for some plots of the projected usage of projected CPU usage at CERN. This, of course, includes all CPU usage, not only Monte Carlo simulation, but as you can see, anything that can be done to reduce this CPU usage would be surely positive. So I want to propose to use GPU computing also for Monte Carlo simulation, because so when you have a GPU, the best thing you can use it for is stuff that is very parallelizable. And Monte Carlo simulations are one of the most parallelizable things you can have. And indeed, most of the simulations are done parallelizing over CPU. GPUs are perfect for this. But however, they are not used, at least not in the phenomenology community. And there are several reasons why they are not, what most of the codes rely on CPU. And I'm going to focus on the 3 reasons that we are trying to address with VegasFlow. So one of the reasons, and probably the main reason, is that during the last 20, 30 years, huge libraries have been built around Fortran and C and C++, which are difficult to port to a GPU, because you have to port a lot of code in order to get results. So if you are interested just in a new process, you can either use the library you already have and modify a small thing and then you have a new result, or you have to build everything from scratch. So obviously, if you want to publish quickly, then you prefer to increase or improve the library you already have, which in turn makes porting the code even more difficult next time. And this brings with it a lack of expertise, just because you have been working on CPU-based code for so long. So you know how to make code performant on a CPU, but this doesn't necessarily work on a GPU. You need to learn new programming language. You have to learn CUDA or OpenCL, which are not necessarily similar to, for instance, Fortran. So it's also a low reward situation, right? Because in order to get the results that you would get maybe in a month with your old tools, now you would take a year because you have to write everything. Which brings me to my last point, which is a lack of tools. While there are already many tools, a complete tool chain for CPUs, there's no such thing for GPUs. And what I mean by this, if we go back to the diagram that I showed before, let's imagine you have a code that does drell-young, and then you say, I want to do a new process, glue-on fusion Higgs production. Then you just need to swap the matrix element to a first approximation. The integrator, the phase space, even the cuts or the pattern distribution function can remain basically the same. But even if you didn't have the drell-young code that you can reuse, there are many tools that you can use that take care of many of these things that you were worried about, right? So for the integrator, you can use Cuba. For the CAS, you can use FastJet. Maybe you already have some analysis written in root. So when you try to do the same on a GPU, you find that you don't have anything, so you have to write everything from scratch. So this is what we are trying to create, a new tool chain that allow developers to also write code for GPUs in an easy way. So I'm going to talk about VegasFlow. We have also created PDFFlow. Marco Rossi will talk about it tomorrow. And this is a Monte Carlo library. So you give it an integer and it gives you a result based on Python and TensorFlow. So the very nice thing is that it's compatible with both GPU and CPU. So if you write your integrand using TensorFlow routines. Then you can test, you can debug on your laptop that maybe doesn't have a GPU. So you don't have to worry about, oh, I have to have this very expensive NVIDIA card in order to actually develop for this library. And once you have everything in place, you can send it to a cluster that has 8 V100, and it will hopefully be very fast. Another nice point is that you are not forced to use either Python or TensorFlow. You can actually interface VegasFlow either with normal Python. You can write your own kernels in CUDA, also C++, obviously. And in the repository, we have prepared examples for each of these cases, so that it's very easy to add new iterants and also new integration algorithm. And the last point has to do with the choice of TensorFlow rather than other libraries that also allow for CPU and GPU kernels, which is the usage of neural network-based integrators that has become more and more researched during the last few years, and that promise a much better performance when doing Monte Carlo integrations. So in VegasFlow, at this point, we have included a plain Monte Carlo algorithm to be used as a template for adding new algorithms. And the important sampling that algorithm that is very well known in the particle physics communities, which is Vegas. And with this, we have started addressing some of the missing ingredients in this diagram. And in the future, we hope also to address some of the phase space or the CATS routine or even the matrix element generation. So the code is available at the GitHub page of the N3PDF project. It can be installed with your favorite Python management tool. And you can also access the documentation at Read the Docs. So now on how to use it is quite simple. So you need to create an integrand. So you decide how complicated you want to do it. In this case, I'm basically summing the x plus x1 plus x2 plus x3. Then you instantiate the integrator. This is similar to how you would use Lepage Vegas library, actually. So you instantiate the integrator with a number of dimensions, with a number of events, and with an events limit, which is the number of events that you send to the device at once. And this is due to the fact that you might have several GPUs, and maybe some of them don't have that much memory, so you want to break your integration in small chunks. Then you compile the integrand together with the integrator. This basically decorates the integrand with the TF function decorator, which here I put it explicitly. And then you just run the number of iterations that you want to run. This will update the grid and so on and so forth. And just to show some examples on how this actually improves performance on a real world problem, we have implemented several processes just to have an idea of how it would do in different situations. So for our leading order process, we implement single top production at leading order. So we run it with matgraph for a target precision, and we get a result. We get an amount of time. Of course, matgraph is not the most efficient of codes because it aims to be completely general. So in that sense, it's not a completely fair comparison. but we also didn't do any GPU specific optimization. So the phase space generation, the cuts, everything is done in an old-fashioned way. And we see a great improvement on the different graphic cards we have tested, but also, and also you see that the kind of improvement you would expect if you join two GPUs. And one nice thing of VegasFlow is that it allows you to very easily and without having to do any work. So the previous code would already do it. Use more than one GPU. But of course, leading order is fairly simple. You don't have divergences. You don't have subtraction terms. So fair enough. And it's a very general code. So we also tested a next to leading order code. So for this, we used NNLOJet, and we implemented the vector boson fusion Higgs production. Again, same caveats as before. The code is a CPU code running on a GPU, really. The only thing that the GPU is given is parallelization. And of course, the integration routine is GPU optimized, but the actual code is basically a port of what we already had in Fortran. And you can see that with this, without any kind of extra optimization, we already get almost a factor of 3 when running with 2 GPUs with respect to running on the full 36 cores of the CPU for the same uncertainty. And this is running an integrand which has 1 radiated gluon, which can become soft or collinear. So there are cuts applied to avoid infinities. There are subtraction terms to control those divergences. And there are phase space mappings, right, from the real radiation phase space down to the 3-level phase space. So this is a proof of concept, of course. It's not the full Python level Monte Carlo simulator, because as I said before, that would be probably a year of work, or maybe a full PhD worth of work. But it's really nice that we are already able to get this performance level with relatively little work on the integrand. So I come to my summary. I hope I've convinced you that that GPU computing is competitive with CPU computing, also for Monte Carlo simulation, also for next to leading order simulation, which well, I've heard time and again during the last few years that doing an next to leading order in a GPU would be impossible because of memory, because of the PDF interpolation, and so on and so forth. And that with VegasFlow you can do this really easily. Thank you very much, and let me know if you have any questions.
Thanks, Juan. Let's see if there are any questions or comments. James has one.
Yes, hello. So yeah, thanks for a really nice talk. I think this is really important actually, because of all of the applications that may be what we might call low-hanging fruit, where we could really make significant gains by porting to GPUs. Event generation is really, one of the first ones you'd think of. Now, I kind of have a dream. Probably it's a very naive dream, but that eventually there might be a sort of a toolkit of the various components that are commonly used in the event generation workflows that different event generator authors might be able to take implement them such that over time, more and more of the workflows could become GPU compatible. I mean, do you think this is something realistic, and is this something you also have in your mind at some point?
Yes.
Yep.
So basically, to a certain extent, this is what we wanted, right? So, well, so some of the plans we have been stopped by the by world events, right? But so for instance, one thing that we were thinking of is to have a phase space generator on GPU, which the phase space generation, for instance, is well, the CPU, the CPU version we have is not the best for a GPU, right? And this, for instance, we were thinking maybe having a master student do it because, well, I don't know how interesting it is for a PhD project, but it could be interesting to start working. But of course, all this stuff has basically stopped. We also, another thing we were hoping is to, and we have had some conversation with the people from MatGraph, right, to generate the matrix element directly for GPU. But all of this is still very in very early stages. But yes, this would be our final goal, right? Our final dream, that you can actually run, let's say, MatGraph and decide I want to run it on my GPU instead of the CPU, and then that you get at least a performance as good as you were getting before. So yeah.
Yeah, thank you. I mean, I know Graham's connected, and I think this is something where the HSF, the HEP Software Foundation, could really help as well, because it's this kind of thing where lots of people need to be brought together. Anyway, thank you very much for a very nice talk.
Thank
you. Chiara, please.
Yes, yeah, it was interesting, this presentation. I wanted to ask you if you could comment on the use of GPUs for simulations that also foresee detector, transporting the detector, so detector simulation and so on, that could use for efficiencies and etc. It was mentioned, I think, a bit yesterday during the session in the afternoon. I'd like you to comment about that if possible.
Well, I don't know really what to comment. So basically, what we have, so the proof of concept we have are only the Parton level Monte Carlo. So we haven't thought about simulating detectors or anything beyond the generation of the Parton level results.
Okay. Okay, thank you.
But yeah, as more tools are developed, surely more and more interfacing of these tools. Basically, hopefully one day we can get to
do everything.
This thing where every tool works on a GPU.
Because clearly for an experiment, for corrections and so on, the bottleneck, if you want to call it like that, is the transporting the detectors. So this is really time consuming.
Yeah, I mean, my belief would be that, so basically the reason we have focused on the Parton level generation is because it was our background. So we have written several Monte Carlo for Parton level, and they are, I mean, I remember during my PhD at some point I was consuming a good chunk of the resources of the university myself. And so we were thinking on how can we do this better.
No, sure. It is.
So
it was a sort of side question. For an extended.
Discussion. It would be really nice to have to have other groups and other people working on the different tools that are needed for a complete tool chain.
Thank you.
Thank you.
Could I make a comment, Concetta?
Yes.
Yeah, go ahead, please.
Cheers. Yeah, so on sort of what James and Chiara raised, I think that what could be very attractive for the experiments is when you want to run a combined workflow where you do the event generation and then the detector simulation in one go. If we can get those kind of workflows able to effectively use GPUs, then I think that's very attractive option, because the more work that we can do on GPUs, the more attractive it becomes for sites to buy them, and then we get a sort of positive feedback loop where more and more of our workflow can be done. I mean, in the end, more cost effectively, and that's what GPUs buy you, is more computation per euro. So I think it's very hopeful that that might go in this direction. Yeah, so for the HSF, so if you, Juan, if you don't know, so we have a working group on event generation, and they have actually been looking at event generation on GPUs, and mentioned rightly the MAD graph. And I know that CERN, people in CERN IT and also the MAD graph authors have been working on that actually this week. There's been a GPU hackathon organized by the University of Sheffield and NVIDIA. So there's progress there. And I think it might be interesting to have a report on this work in that forum as well. I had, so moving on from those general considerations, I had one very practical question, which is about which version of TensorFlow do you actually use?
So we have developed, we developed it under 2.1. This plot is done under 2.2.
Yeah.
And this one is done under 2.3.
Okay.
So for now it works in all three versions that have come out this year.
Right. Okay, that's good actually. I think what I was mainly driving at was whether you were in TensorFlow 1 or TensorFlow 2, because I know from other projects, for instance, like ZFIT, that use TensorFlow, they started development earlier in TensorFlow 1, and it was not that easy to move to TensorFlow 2. So if you're already there, I think that's a good thing.
Yeah, we have some other projects that had to be ported, and yeah, it was a bit of a nightmare at times. That's why now every time there's a new release, I test it just to make sure that the amount of things I have to change are as small as possible.
Yeah, thanks very much.
All right. Yeah, I cannot but agree on the general comments that was made about the usage of GPUs in our simulation workflow, taken from a global point of view, including generators, particle transport. I mean, there are some activities that have started in this domain, but it's clear that we can do much. We can do much, and then we can profit from whatever resources, whatever accelerator could be offered to us in our distributed computing environment. So this is some kind of process that has to start, and at some point it will eventually start. I don't know if we will be forced or we will be gracefully going there, but we'll see. But this will eventually happen at some point. So, all right. If there are no other comments,
I stop sharing.
Okay, thanks again, Juan, and I would like to thank all the speakers for their very interesting and nice talks that we heard this morning. So if there are no other points to discuss or general comments, I would take the session to an end and remind that there will be another session tomorrow morning at 8 o'clock again, and will be the last session of our track. So thanks everybody for attending.
Thanks, Concetio.
Okay.
And,
thank you. Bye-bye.
talk to you tomorrow. Bye.
Bye-bye.
Bye-bye.
Bye.
Bye.